everybody, to the second half discussion of Chapter 11. So let's go ahead and get right back to where we were at, where we left off. And we talked about, can't remember if we talked about this or not, but I'm going to explain it once again. Actually, I think I did cover this, but I'm going to explain it once again anyway. So in our discussion of how we can design digital circuits and how these circuits work and how to make our life easier, one of the things that we can do is we can use our knowledge of analog circuits to create an automatic power up reset when we flip on the power to use this 7476, okay, with these JK flip-flops inside. There's two of them. Okay, so we have this on the asynchronous reset, and remember, that's an active low input in both cases. So what happens is the power is at 0, RD is at 0, right? So it's low right now. And so when this gets turned on, when it activates the chip, okay, initially, because this capacitor takes time to charge, initially the resistor here drops all 5 volts, and this drops nothing, which means it's a ground. So essentially it's still connected to ground here as a low. Well, when this initially starts up and those two are low, that's going to reset both flip-flops, both JK flip-flops. And then what happens is, as this capacitor charges, we know from our RC time constant work that all the voltage is going to shift from the resistor over to the capacitor. Okay, and then once the capacitor has all the voltage, this becomes 5 volts right here at this point. And so that means that there's a high. So on that RD is a low that charges to a high until you open the switch and turn it off, and then it will discharge. Okay? So that way, when you power this up, it automatically starts both of your counts at your Qs at 0. Okay? So that's just a neat little trick that you can use. So let's talk about Schmitt. So the Schmitt Trigger ICs are very much a solution to what we talked about with the transfer curves of the TTL and also the CMOS, where you have sort of a waterfall effect or a slope effect. Okay, what the Schmitt IC tries to do is tries to put a nice crisp 90-degree turn on both the low to high transition and the high to low transition. Okay, and the other nice thing about the Schmitt trigger is because it has a hysteresis, it has a hysteresis where you have a forward going voltage and a backward going, or a positive going voltage and a negative going voltage. It reduces the amount of noise, it reduces the amount of an effect the noise has on the signal. So you can see here in this diagram, one of these, this is the same source here, digital pulse, and then they throw some noise on there just to see how each chip deals with it. The 7404 performs like this, okay? It's got a single switching threshold to where, you know, it determines whether the input is a high or a low, okay? And obviously when it crosses that threshold, it inverts the output to whatever is the opposite, okay? If you have a single threshold like this, what happens if you do have some noise? As this digital pulse is trying to go high and you add some noise in there, if it keeps switching back and forth across that threshold, then the chip is going to assume that you are changing from high to low, and the output will change accordingly. So there you've got a couple little glitches on the line, and here you've got a couple little glitches on the line, because really what you wanted to happen was when this thing transitioned high, it's one thing, and then it transitions low, and so you just have the pulse. So this is mimicking what would happen in the real-world scenario, like if you were in a factory or something and you have a lot of three-phase, 480-volt motors running, and you have a lot of kind of static electromagnetic noise in the air. Sometimes that gets picked up on a conductor and transmitted with whatever signal is on that line. So if you just have that single threshold like a typical TTL 7404 inverter, then it could pick up that noise and cause some little glitches here, cause some unwanted actions. However, if you have, as I was trying to describe before, a positive going voltage and a negative going voltage, it gets rid of that scenario where you have that noise that's fluctuating up and down in very, very small amounts. So here, initially the inverter is high, so that means the input is low, right? It crosses the lower threshold and then goes back under the lower threshold. It doesn't invert until it goes to the positive going. So when you're going from low to high, that you have to hit that top threshold for it to invert. Okay, now you can see it goes all the way to the top, it stays high. Now down here, it switches, it goes below the positive threshold and comes back down, but it does not invert until it hits the negative going threshold. Okay, and then it inverts. So you see here, this is more representative of what we wanted with this signal, okay, when we invert it. So when you're going from low to high, you have a positive going threshold that you have to cross. And if you are going from high to low, you have a negative going threshold, right? And we call that hysteresis. Switching thresholds of positive and negative going signals are different. And like it says here, useful to ignore small amounts of jitter or electromagnetic noise that may be on the line or whatever, okay? And here's the transfer curve, okay, the transfer function. So this is what we were seeing in multisim, right, where we saw the, it looks like almost like a hurricane symbol or something. What it's saying is while you're at this high voltage, if you're going to transition low, okay, you have to reach this voltage down here, right? So if you're going to go from high to low, you have to follow this path, okay? And that is a 1.7 volt positive threshold. If you are at a low signal and you want to go high, you have to come all the way up to, or you have to come down to the negative voltage of 0.9, and then you can transition, okay, and invert up to the high. Because remember that we're looking at an inverter right here. That's why it looks backwards, right? So, you know, when we're going from high, this is really a high up here, right? That's being input because it's transitioning to a low. And then when we put the low in, the negative going is 0.9 volts, and it'll then invert the signal up to a high. Okay. So anyway, this is what the third function would have looked like if we would have done Lab 9 in face-to-face, or if you've done it face-to-face, you would see that the Schmitt operates like this with a hysteresis, whereas the TTL is more of a waterfall. And the CMOS almost looks like it's not a nice curvy waterfall. It almost looks like a straight line, like a slope. But the Schmitt, again, you have these nice crisp lines, and you also account for some of that error. All right, so here's another way to look at it. So we're looking at the signal before it gets to the Schmitt, and we're looking at the signal after it's out of the Schmitt. So the input and the output here. And you can see, if we mimic the input, and we have a triangle wave that climbs, you can see that the positive going threshold is when it switches. It comes to its peak, comes back down. It doesn't switch here. Where it hits the positive, it has to hit the negative going threshold, and then it transfers. Okay, and it switches. Right, so these two things you really need to understand. So if you need to walk yourself through how these work again, make sure that you do that. Okay, it's very important. All right, switch debouncing. So another thing that happens, another source of error potentially, is the fact that when you throw a switch, and it could be any switch, it could be the light switch in your house for that matter. Anything that's a single pull, single throw, or, you know, like in the case of the Altera boards, like if it's a toggle switch, you can get the same effect sometimes. Push buttons do the same thing, but this one is a single pull, single throw. So when you throw it, it stays where it's at, okay? Now, the problem is not when the switch opens, right? When the switch opens, it might bounce back here, very, very small oscillations. The problem is when you close the switch. Now, we don't think about this because we don't care about what happens in the nanoseconds that follow that switch being pulled. We know when we pull the light switch, the lights turn on. That's it. That's as far as our analysis goes. But if you look into the transient period, right after the switch is thrown, what you'll find is that switch actually bounces because of the mechanical energy pushing it forward. It will actually oscillate slightly until it burns out all the energy, and that's represented here. So here we close the switch, it hits and bounces. So the switch physically oscillates and bounces until it dissolves all that energy, dissipates all that energy. Okay? Now, that's a problem for something that's not been debounced, because that could be accepted here. You know, this is a JK flip-flop that's set to be toggled. It's got a high and a high on the J and the K. And we've got a little pull-up resistor here to make sure that we get a high when we need it. But anyway, this is set to toggle, so it's going to go high and low, high, low on the output. And you can see here it's picking up all of those bounces as a transition from high to low and causing the flip-flop to operate in a way that we don't want it to. So, right, this is the clock pulse, sorry. We get all these clock pulse entries here, and that transitions to the Q down here, right? But it's still operating out of control. And you can see how it continues to oscillate. So to prevent this from happening, okay, we can put in some debouncing circuitry, and this is about the simplest way to do it. So we have a pull-up resistor that goes to 5 volts, and then we've got a pull-down resistor connected to a switch, which is connected to ground. And then we've got a small capacitor here that's going to allow us to make sure that we have that 5 volts charging here, okay? So while the switch is open, the only thing that this circuit is doing is going from the 5 volts to the ground, and it's charging. It's just another RC circuit here. Initially, all the voltage is on the resistor, and then eventually it transfers over here to the capacitor. All right. So initially, it's going to be high. The V output is going to be low because this thing is going to be charged high. When you want to switch it and you click over here, now this thing can come down to ground over here, right? Because it's just going to take this resistor over here because it won't be able to flow through this capacitor because this capacitor is charged to 5 volts. But here it has a clear path to ground, so it's going to drop the majority of the voltage here, and then this will be a very, very small voltage drop over here to get the current to flow down to this ground. Okay, so, but when that switch gets punched or when it gets turned on, it's going to bounce a little bit. But because you have this capacitor here that is, getting these small charges and discharges because of where it is, that's going to smooth out those transitions. It's almost like a shark fin, right? So instead of getting the full jump up here, it has to charge. It can't just charge automatically. So it takes a little bit of time to do that. So we actually use that to our advantage, and this will actually debounce that switch, and then you have a nice crisp output as a result. Okay, because that's the whole point. We're trying to get rid of this bounce right here. This is one way to do it. This is another way to do it. So here we have a selector switch that no matter which way you throw it, whether you're going to A or B, you're always going to have switch bounce because one direction is turning it off, right? And more than likely it's not going to bounce all the way back and hit the contact. But here you're smacking a contact every time you move the switch from A to B. So here, apparently we're starting at the switch at A, and then we have a set condition on our output. So A is high, and then we go, boom, we switch it over to B. All right, but when it hits B, it ricochets back and forth here and oscillates just a bit. All right, because we have this cross-coupled NAND scheme in here, it prevents that from adjusting the output, okay, to something that we don't want. So as soon as it hits the low here, it's in a constant reset, all right, reset condition, and up here it's in a constant set condition, all right. So this cross-coupled NAND scheme prevents that bouncing from changing the output, all right. This is yet another way to do it, is with a D flip-flop, and just have each one of these selectors tied up to a set and a reset, and then here is your voltage out as well, all right, for a Q out. And so you have essentially the same setup here. So what you're going to do is you're either going to send a low to this side, and this side will be high, or you're going to send a high to this side, and this side will be low. So only one of the two is going to be active at any point in time. All right, so walk yourself through this. If the switch is over here at B, that means that I have a ground right here. So that 5 volts is going to drop across that 10, and this is going to be 0. Okay, because I have a place to ground that out. So this all is 0. This entire node down here is 0, which means a 0 is going to be on the reset. Okay, at the same time, I don't have anywhere to ground after resistor here, so this is just basically one big conductor from here to here, and it's all 5 volts. It's all high. Remember, if you have an open circuit, resistors become essentially a conductor. So this is 5 volts the whole way across here. So that's one condition. Then if you move it over to A, exactly the opposite happens. Now there's no way to drop that 5 volts across the 10K. And so this entire thing is all 5 volts because it's just one big conductor. However, now you can drop the 5 volts across this 10K, and you have a ground over here that you can get to, right, to let the current get to ground. So now this side would have the 0, and this side would have the 1. So it's just going to flip it back and forth based on where this switch is. Okay? And this is what it would look like if you were to do that in Cordis. Okay? Now this is an older version of it, but the symbols really haven't changed in 15, 20 years. So this is debouncing multiple lows on asynchronous inputs. So it's the same concept. Right? And here they even put in a little bit of bounce to show you that the output would not be affected by it. Right? And so you can do this. When I do the next Cordis video, I can show how to do little sections like this where you can add in bounce or build this one for yourself and then put this kind of an input in and see that it works. So I keep talking about the pull-up resistors and the pull-down resistors. And so if you use a pull-up resistor, the whole thing is you're trying to bring the voltage threshold up of some output. Okay? And usually we just hook 5 volts with a 10K ohm resistor. That's the standard value. And if we have a pulled down resistor where we want to make sure something gets pulled low, we just use a series 100 ohm resistor and connecting that directly to ground, okay, to keep something low. But there is going to, because it's a 100 ohm resistor, that's not very much resistance. However, it is going to cause a small voltage drop, and there's going to be a little bit of current associated. So you're going to have almost like a leakage current if you use a pull down resistor, like it says here, high power dissipation, because you would have to keep this low, you would have to have kind of a high current, okay? Or you would have a current that's constantly running anyway. Okay. As far as all of these practical considerations, I'm just going to walk you through some of these, and then we will be done with this session. If you want to learn more about each one of these, you can go into the Kleitz book, and he explains them in detail as well. And it's just in written form instead of me explaining it. So this is one I do want to point out, because if you wanted to build your own little 5-volt power supply, when this says 1,000 microfarads, you could really just, that's just 1 millifarad, okay? So here we've got 120 volts, 60 hertz coming out of the wall. In the United States, that's what we have. That's the electrical service that we have. In other countries, it's sometimes I think they just do straight 240, and some countries have 50 hertz instead of 60 hertz. Just depends on what country in the world you're from. And sometimes if you take your laptop to some other country where they have a different plug-in for one thing, and then they also have a different frequency they use, you have to put a little adapter on your plug, because you can't run an American-made device on a 50 hertz. You'll destroy it, or you'll burn out at least some of the components. So anyway, so 120 volts, 60 hertz, that's what comes out of the wall here. Hopefully you've got your primary side fused somehow so that if you have a problem, it doesn't blow up. But anyway, this is just a roughly a 10-to-1 transformer, 120 volts down to 12.6. And then we've got a full wave bridge rectifier here that you could just buy, or you could use 4 diodes, right? So it says here 4 of the IN 4001 silicon diodes, or just a single 1 amp bridge rectifier. Either way, you'll learn about this in 121 if you haven't taken that class already. But anyway, essentially what it does is it takes the negative half of the sine wave and flips it around and makes it positive. So instead of going high, I'm doing the sine wave right now, right? It goes up and then it comes back down, under and then up. So what it does is where it goes under here, it just flips it and makes the whole thing positive. So really what it does is you got these humps, these positive humps, instead of going under and going negative. And then these capacitors and this voltage regulator help smooth out those transitions to where essentially it stores and you have 5 volts out here, okay? And so that would be caused by the regulator here, because right here you should have 12.6 volts, okay, is what is on the output there. So, anyway, this is an easy way to get a 5-volt signal out, right? And then the next part of it is, maybe connecting up just a Schmitt right out of the secondary of a transformer. Couple of 1K ohm in series with the 2 leads, put a Zener diode in to get the 5 volts out, and then this will give you the nice crisp lines. It'll take the sine wave and actually make it a square wave, okay? And this is actually TTL level if you use the same transformer. So these are the kind of little projects and little examples that Kleitz uses in Chapter 11, last part of Chapter 11, okay? So you do not have to do these. I'm just pointing out that if you wanted to, you can even build this stuff like in Multisim. Some of it you can build in Quartus. So like here's one. Here's it says driving light emitting diodes. And so you can have on the output here, remember, an LED has to have a current limiting resistor in series with it. And so essentially what this is doing is either allowing this a place to have a voltage drop and generate current that's going to sink, or it's going to be a high on the output and there's nowhere for this to go, all right, and it's going to turn it off. So it's going to blink on and off based on this 1 pulse per second clock. So it's going to be on for a second and it's going to be off for a second. It's going to be on for a second and it's going to be off for a second. If you had your own, let's see, is there any that you can, yeah, there is. On your DE10 light, you've got 8, well, those may be input ports. No, they're I/O. So you can make them output. So my whole point in that is that you could, if you want to, you could set up your DE10 light to blink a light out of one of these flip-flops. So, I don't know. I might mess around with that and see if I can figure it out. I haven't tried it yet, but you could. And just do a simple little blink here. Because all this is a 1 pulse per second clock. You could put that in Quartus if you wanted to. Okay. I don't know how much of this I really want to... I guess I'll talk about this one first. So here's the clock input to a D flip-flop, and it says photo transistor input to a latching alarm. So once the alarm is on, you have to go manually hit the reset to get it to stop. Because notice here that there's only a single input and it's high. So there is no transition back to low on this D flip-flop, because once it gets set, that's it. It latches high. So you would have to manually hit this reset to give this a 0 and allow it to work. So this transistor, and this is not an analog class, but anyway, if you have sufficient current on the base, it will provide a short from C to E. And essentially you can drain current through there. You can sink current through there. We talked about that in Chapter 9. So this is a photo transistor. So instead of just having voltage or a current on the base that's high enough to drive it, it's connected to a photo cell that if there is enough light that can be converted into an electrical signal, it will turn this on. So essentially it's light dependent to turn the transistor on and create the short, and then you can sink down to ground. Okay? So that signal is either going to be high or low. That gets set through a Schmitt and then through a Schmitt again, so it inverts and it inverts again. So it creates a little pulse. Okay? So it says high pulse when the light is interrupted. So if it's high, then this thing should be low all the time. Okay? But then if it turns off and then comes back on, it will record that little blip here into the clock pulse. It'll make a transition and it'll lock that one into the flip-flop and then turn this thing on. Okay? So, and then once it blips once, it doesn't matter how many times it does it. As soon as the light's not there, it turns this alarm on, and you can only reset it with the reset button. Okay? So, if you're bored, you could build some of this stuff. Another optocoupler. There's a almost you have an eye, like an LED that shines, and then this thing turns on if this thing shines on it. So you almost have like a wireless switch, so to speak, because you're using light to turn something else on, even though there's no physical connection there. Oh, I think that's all I want to say about those. So just to recap, we talked about, originally in Chapter 11, we talked about the timing requirements, where you have the setup and the hold time that have to be met. You have the propagation delay. You have the pulse parameters. You have a hold time, a setup time. I said that already. Changing voltage on a capacitor in series with an RC circuit can be used, and a series RC circuit can be used to create a short delay for a power-up reset, the automatic reset. That's kind of nice. And the two key features of Schmitt triggers is that they have very sharp 90-degree edges, and they have hysteresis, which means they have two distinct input threshold voltages, meaning they have a positive going voltage threshold and a negative going threshold. And there it is, the hysteresis. Mechanical switches exhibit a phenomenon called switch bounce, which means that when the switch actually makes physical contact, it bounces slightly. There's an oscillation. And we talked about pull-up resistors versus pull-down resistors. If you want to force something high or if you want to force something low, those are what you would use. And we use a 10K and a 100 ohm. A 10K for a pull-up and a 100 ohm for a pull-down. And so we also went over the practical, inexpensive 5-volt power supply that can be made with a transformer. Now, here's the thing. If you're going to build one of these, don't just grab a transformer from some device, okay? That transformer was built specifically and chosen specifically for that particular project. And nothing makes me more nervous than watching a video on YouTube or somewhere where people are just grabbing transformers out of random devices and then trying to use them for some other purpose that may cause them to short out or explode or have some other bad accident. So if you want to do something like that, just buy a transformer and buy it knowing what the ratio is, buy it knowing what the specs are. Buy the diodes and the capacitors from the same place. I usually go to DigiKey or Mauser or someplace like that online. There's probably even, if you just search for 5-volt power supply schematic, I would probably take whatever I find on the internet and make sure it works in multisim first before I, go blowing something up. But anyway, it's very, very easy to make a power supply like that with just a few components. And that 5-volt power supply could be used to power anything. So it could be used to power your IC chips if you wanted to buy some TTL chips and buy some CMOS chips too. All of those chips require 5 volts to operate. You could also use it to drive an LED because an LED only needs a 300 ohm resistor and 5 volts for it to operate. So just some things to consider. And they're talking more about the other circuits. Okay. So that ends the discussion on Chapter 11. So that takes us through 9, 10, and 11. And so now you will have an exam. So come back to this when you want. There's going to be a separate video for Cordis operation, and that you can find on YouTube as well. Thanks for watching.